Hello and welcome to the third section of the theory and applications of network coding class. In this session we will talk of applications of network coding in wireless settings, and we will consider several relevant wireless network coding problems. So we will consider two settings. One is ad hoc wireless multi-hop networks in which information is delivered to different clients over multiple hops. And the second is heterogeneous wireless network settings in which each device has two interfaces. One is cellular interface, which allows to receive data from a base station over a long-range cellular network. And the second interface is a local wireless interface, which allows the node to receive data over the local wireless network, such as a Wi-Fi network or a Bluetooth network. So we'll see in both networks the principles of network coding will allow to receive data more efficiently, in particular in cases in which clients are interested in the same data. So, for example, consider settings in which all of those three clients, they want to watch a movie or receive a file, and suppose this file is broadcasted from the base station. However, so suppose in this example the file just is divided into three packets, and those three packets are broadcasted by the base station to those three clients. However, due to erasures and packet loss, some of the clients will missing packets, right? For example, client number 1 is just missing packet number 1. And in this scenario, the network coding can be used to exchange data over a local network. So this will correspond, as we'll see, to problems which we called cooperative data exchange problem. In this problem, initially we have some certain ground set of packets, x1, x2, x3, and x5. And each of the clients initially holds a subset of packets. For example, we see that client number 1 have packets x1, x2, and x3, and client number 2 has packets x2, x3, and x4, and so forth. So initially, each of the clients have a subset of the packets, and the goal is for clients to exchange those packets over a local wireless network, such that in the end of the transfer, all of the clients will be able to access all packets. So in this case, we can see that client number 1 is missing packets x4 and x5. Client number 2 is missing x1 and x5. And client number 3 is missing x1 and x2. So if we want to transmit those packets uncoded, we need to make at least 4 transmissions. We need to transmit x1, x2, x4, and x5. We don't need to transmit x3 because we are lucky and x3 is available in all clients. So with wireless network coding, we can reduce this number of transmissions from 4 to 3. Indeed, for the following transmission scheme, in which client number 1 transmitting x1 plus x2 plus x3, and client number 2 transmitting x2 plus 2x3 plus x4, and client number 3 transmitting this combination, we will see that all clients will be able to decode all packets. So regarding the operation of addition and multiplication, here we can assume that this is performed, for example, over some finite field, which for now can be a prime field with relatively large prime. So all operations here, addition and multiplication, are just operation over this field modulo this prime number. So now we can verify that with network coding, each of the clients can be able to decode all packets. For example, consider client number 3. It already has packets x3, x4, and x5. Then it can use transmission from client number 2 because it can receive from client number 2 x2 plus 2x3 plus x4. Now it can substitute x3 and x4 in this transmission and decode packet x2. So now client x3 knows packet x2. Now it can substitute x2 into this combination transmitted by client number 1. And also can substitute x3, which is already known to this client, to obtain x1. Now we'll see that client number 3 will be able to obtain both x1 and x2. Similarly, we can see that each of those clients can be able to obtain all of the packets it needs, and we only need 3 transmissions over this broadcast lossless channel, and it constitutes a significant advantage over uncoded transmission. So this advantage is even more evident if we have a larger number of clients, and each of those clients can missing only a small number of packets, which can be different from every client. But so suppose we have just a random packet loss in each client, so each client has just a random combination of packets transmitted over the channel. In these settings, network coding can have a significant advantage rather than doing it in an hard-coded way. So what we see here is that network coding can help in this scenario of heterogeneous network, in which clients jointly want to receive some packet transmitted from access point, but some of the packets are lost in transmission, so we don't need to go back to access point and ask to retransmit, but we can use this information. We can use information available at other clients, so clients can cooperatively recover all the packets they need. Another setting which was recently considered by a researcher from University of California at Irvine is called microcast. In this scenario, the group of the users, they want to download jointly a big file from base station, but file is not initially broadcasted to the users, but rather than divided into chunks, which can be overlapping chunks, and each of the users will be responsible of downloading a certain subset of those chunks. For example, here client number 2 is responsible for downloading P2, client number 1 is responsible for downloading P1 and P3, and client number 3 will be downloading P3 and P4. Once this download is done, the client will exchange those local packets such that in the end everybody will know everything. So it also can be seen that in order to download those packets, to exchange those packets in a robust and reliable manner, the network coding can be beneficial to be able, to ensure that each of the clients will be able to decode all the data it needs with a minimum number of transmissions. Let us consider another version of this problem, which is called secure data exchange. In this case, the information transfer is performed in the presence of an adversary that can listen to the packets transmitted over the broadcast channel, and the purpose of the adversary is to be able to decode individual packets. So we have a grand set of packets x1 to x5, and the notion of security that we use is called weak security. In this case, what we require is that mutual information between any individual packet and the set of packets P transmitted over the channel is equal to 0. So this notion of security is in contrast to much more strong version of what we call strong information theoretic security. And with strong security, we require that mutual information between the entire set of packets and set of packets broadcasted over the channel is equal to 0. However, to achieve the strong security, we will need a much more expensive solution in which we need to have some random keys shared among those clients, and which can be prohibitive in practical settings. With weak security, we only protect individual files. So for example, here, if adversary receives 3 linear combinations, it cannot use those 3 linear combinations to decode any of the files here, right? So you can verify that it will not be able to solve this under constrained system of linear equations. With 3 linear equations, we cannot decode any of the packets individually. It can only obtain some information about some combinations of 3 or more packets. So in this case, it can be useful in practical settings. For example, if those packets are originally some random variables identically distributed over some finite fields, and if adversary receives some combination of those packets, it's much less useful than original packets, right? So if I'm receiving some combination of compressed emails, it will give me really little information about any individual emails. Therefore, this can be useful. So what we can see here is that, first of all, network coding definitely gives us an advantage, because not only it allows us to reduce the number of transmissions, but will allow us to make those transmissions much more secure, right? By combining those packets, we'll prevent the adversary from being able to decode individual packets in this system. This problem is related to the secure secret sharing problem. So suppose those packets are not data packets but secret keys. And we want to obtain, so initially each client has some set of shared keys which can be overlapping, but what we want to do, we want to obtain a set of keys which are known by all clients. So initially here we see that one of the keys, x3, is known to all clients, and this is initially, but what we want to do, we want to basically obtain another key that will be also known by all clients. And this can be done through the secure data exchange. So for example, here we see that after 3 transmissions, all of those 3 clients, they will know an entire set of 5 packets, x2, x1, x2, and until x5. So all of those clients will know entire space formed by those 5 packets. An adversary will only know the subspace of dimension 3, which is formed by the clients transmitted over the channel. An adversary can listen to every client, every packet transmitted over this channel, so it will know the subspace of dimension 3. This implies there are 2 vectors, right, that we have 2 degrees of freedom that all of the clients can to obtain, which will not be known to the adversary, right, because adversary only knows a subspace, so we can identify 2 vectors which will be known to all clients, because any vector is known to all clients, but those 2 vectors will be, for example, orthogonal to this subspace. So for example, a null space of the subspace, orthogonal subspace, will not be known to the adversary, and those bases of the subspace can serve as a set of secret keys. So we'll notice that in this case, the problem of minimizing number of transmissions is well aligned with problem of distributing shared keys. The fewer the number of transmissions, the less information is known to the adversary. So this is another interesting problem that we will discuss later on in this class.